Hello students, welcome back to Best Academy. Today I am going to discuss a new topic. Last time we have discussed how you can find out the eigenvalues and eigenvectors of a matrix. Today we'll discuss how the matrix is diagonalizable or not. What is the possibility of diagonalization of any matrix? So let's start today's lecture. For example, we have an example. Determine the matrix is diagonalizable or not. So today's lecture, we start this lecture solution. First we find the eigenvalues of this matrix. So I considered it as let A is equal to 3, 1, 1, 3, right? So this is the matrix. First we find the eigenvalues. For eigenvalues, we know that for eigenvalues, determinant of A minus lambda I is equal to 0, right? First we find out its determinant. So we can written as A minus lambda I. So that is equal to, basically we can written as 3, 1, 1, 3, which is equal to lambda 0, 0, 0, right? So here we obtain that 3 minus lambda 1, 1, 3 minus lambda, right? So now we find out the determinant. Determinant of A minus lambda I. A minus lambda I. So here is the determinant is 3 minus lambda square minus 1, that is equal to 0, right? So we can written as this equation, that is lambda square minus 6 lambda plus 8 is equal to 0. And if you're going to solve this value, we'll obtain the first lambda 1 is equal to, here we'll written as lambda 1 is equal to 4 and lambda 2 is equal to 2, right? We have obtained two eigenvalues, which is required eigenvalues, right? Now we find out the eigenvectors, right? Now we find the eigenvector. Let V1 be the first eigenvector corresponding to eigenvalue, that is lambda 1 is equal to 4, right? If lambda 1 is equal to 4, we're written as this equation, that is n equal to A minus lambda I, right? If you want to put this value in this pair of expression, so we obtain, here is 3, 1, 1, 3 minus, here is lambda is equal to 4. Sorry, here is lambda, here is 4, 0, 0, lambda 4, right? So if you're going to solve these values, we'll obtain, here is minus 1, 1, 1, negative 1. If you notice that here is n A minus lambda I. So we have obtained the matrix x1, x2 is equal to 0, 0, 0. Basically, this is the basic definition to find the eigenvectors, right? Basically, null of that vector is equal to 0. So now we try to find the first eigenvector. In augmented form of this matrix, we are going to written as, that is minus 1, 1, 1, minus 1. So here is 0, 0, right? If you're going to multiply, the first term is minus 1, R1, right? And second step, minus 1 R1 plus 8 in R2, right? If you're going to written as, if you notice that, here will be obtained minus 1, here is minus 1, here is 0, here is 0, here is 0, here is 0. The reason is that if you have the same values, so this term will be 0. So we can written as this, for example, obtain that is x1 minus x2, which is equal to 0, right? This is the x2 is a free variable. Now you can choose, or depends on your possibility, your desire. If you're going to put this x1 equal to t, this must be equal to minus t. If you're going to put this value, let x2 is equal to t. So we obtain the value x1 is equal to t. So in vector form, we can written as this x1, x2. So we have obtained the vector like this way, 1, 1, t, such that t belongs to real number, right? So we have obtained the first vector, which is the span of this vector. So we have obtained the first vector, v1 is equal to 1, 1, right? Now we put the second eigenvalue. Now we find out the second eigenvector corresponding to second eigenvalue. So we can written as, I'm going to put the direct expression for lambda equal to 2, right? You're going to put this value in the expression. We can written as 3, 1, 1, 3. Here is 2, 0, 0, 2, right? So we obtain the term that is 1, 1, 1, and 1. So in written as augmented form of the matrix, right? If you multiply the first term, obtain minus 1 R1 plus 8 in R2. If you multiply this term, and you have noticed that two rows are same. When two rows of in matrix, any rows of the matrix and its matrix are same, it means all other are 0 except 1, right? So here this case obtained like this way, 1, 1, 0, 0, here is 0, 0, right? Now I'm going to remove this side, right? And find out of here is further detail, right? Here I'm going to repeat this side, right? We have obtained this value. Here is x1 plus x2 is equal to 0. Again we have in x2 is equal to free variables. Now we choose it, let x2 is equal to t. It means that we have obtained the x1 is equal to negative of t, right? So we got an eigenvector like this way of an expression, that is written as negative of 1, 1, and t belongs to set of real numbers, right? So if you're going to written in the matrix vector form, eigenvector, we have obtained negative 1, 1, right? Now we define a P matrix, right? The P matrix is basically the vector in which you have eigenvectors. The matrix in which you have eigenvector. This is your first eigenvector, and this is your second eigenvector. P is always defined as. So the question is that determine the matrix is diagonalizable or not. You can easily understand from this condition. For example, you have 3 eigenvalues. You must be 3 eigenvectors. In my case, here I have obtained 2 eigenvalues. And corresponding to eigenvalues, there is 2 eigenvectors. And we can written as in the matrix form, right? So if you have 2 eigenvalues, there must be condition is that must written in the form of 2 cross 2 matrix. You have 3 eigenvalues, there must be important condition, there must be 3 eigenvectors, and P matrix should be 3 cross 3 matrix, right? So we can written as here, so matrix is diagonalizable. Right. Now we find out the diagonalization condition. For diagonalization condition, we understand some condition. What is the important condition for diagonalization? For diagonalization, there is an important condition is that A is equal to PDP inverse, right? Here is a P matrix, we'll take his inverse, and D will be a diagonal matrix in which we have eigenvalues. So I'm going to define the D matrix in which I have eigenvalues. The first eigenvalue that was for 0, 0, 2. D matrix is that matrix in which we have eigenvalue in their diagonal side, in principal domain, cross diagonal values, right? Now we're going to find out P inverse matrix. You're going to find the P inverse of this matrix. So notice that here will be, that is adjoint of A divided by determinant of A matrix. So if you're going to put the values in this expression, I will obtain the values like this way. 1 by 2, here is 1 by 2, that is negative 1 by 2, there is 1 by 2, right? So this is the P inverse matrix. Now we put all these expression in this equation star. If left hand side of the matrix, if this expression is equal to this expression, we can say that matrix is diagonalizable. Now we check the diagonalization of this matrix. I'm going to remove this side. Right. Now we put all those values. Here you notice that on the left side of an expression, there is a matrix. For example, that is 3, 1, 1, 3. Right. On your left side, here is the P vector. And we have the P matrix that is 1, negative 1, 1, 1. Right. And second matrix is D matrix. D is basically that matrix in which we have eigenvalues in our diagonal system. So we have 4, 0, 0, 2. Right. And this is your P inverse matrix. So we can written as here 1 by 2, 1 by 2, minus 1 by 2, here is 1 by 2. Right. If you're going to multiply this side, right, here is 4, 1, here is 0. The first term is here is, then your second term, that is 4, right. If you go to the second term 0, that is negative 2. Written as same here, that is 4, and this term is 0. Now this multiply, it is 2, right? So now we multiply 1 by 2, 1 by 2, negative of 1 by 2, it is 2, right? If you're going to multiply the first term of an expression, this term you will obtain 2, and you're going to multiply by this term, the first condition will be satisfied, that is 3, and second is 1, 1, 3, right? So if you notice that this is a matrix which I have obtained your left hand side of an expression of the matrix. So left hand side is equal to right hand side. So the matrix is diagonalizable. So matrix is diagonalize. So this is your basic procedural way. You can find out the matrix, whether the matrix is diagonalizable or not. You can easily find out the diagonalization of any matrix. But remember one thing, the diagonalization condition when you have square matrix. If you have square matrix, it means you have. So this is your basic procedure. You can find out the diagonalization of any matrix. But remember one thing, if you have square matrix, then you can find out the diagonalization. Otherwise not possible. In other case, for example, you have square matrix, right? Some cases, if you have square matrix and you have multiplicity, but sometimes you have some eigenvalues, you can't find out the diagonalization of any matrix, right? This is your basic procedure. You can't find out any diagonalization of the matrix except square matrix. The reason is that you have some n cross n, which means that when you have n equal to n, it means the matrix is square. When matrix is square, that means that you're going to multiply some eigenvalues, that is basically lambda times I. I is basically notation of identity matrix, which shows that your matrix should be square matrix, right? When matrix is square, then you can find out the eigenvalues, then you can find out the eigenvectors. Then you find the vector matrix P. Matrix P tells us whether the diagonalization possible or not. Here I'm going to stop my lectures. You have any sort of query, any sort of question about this topic, you give me a comment. I will discuss your all sort of problems in next video. So see you shortly till next video. Bye bye. Have some eigenvalues. Then you can find out the diagonalization of any matrix. Right?